Excellent. Thank you very much for inviting me to take part in this absolutely astonishing event. And also thank you to everybody for hanging around after Bernard's wonderful talk and actually continuing to listen to me. So I'm going to be talking a little bit about a project that's been running for about 20 years now, almost as long as the Hands-on Universe has been around, looking at how we use robotic telescopes to help share the excitement that we find with doing science with as many people as possible. So I'm going to be talking about how we use astronomy in education and how we were driven to do this by a challenge. There is a big challenge in education at the moment that very large numbers of young people turn off. They lose interest in science and technology and engineering and all these areas. And some of them lose interest in arts and humanities, but there seems to be a turning off at teenage ages. And that's true over most subjects, but it's less true for astronomy than any other science. There's been a lot of research into this. There's an example of a paper here, that astronomy is essentially the science that appears to continue interesting girls and boys of all ages for as long as possible. And so 20 years ago, we started looking at this and thinking, well, can we use that? Can we use that fascination, not to promote astronomy, because frankly, we don't need to, but can we use that fascination, that interest, to help teach and enthuse everybody about all of science and beyond that, into computing, into engineering, into art? Can we use astronomy as a tool for teaching? And our toy for doing this is this rather lovely thing here. This is the Liverpool Telescope, not in Liverpool, for obvious and hopefully for obvious reasons. I've just looked outside the window here. I'm just outside Liverpool. And although the forecast today was for bright sunshine, it's raining. This is not unusual. So we put the telescope somewhere else. We put it on La Palma in the Canary Islands. For those who don't know La Palma, it's this one here. And the observatory itself is at the top of the ridge of this eroded extinct volcano to the north. There's an active volcano to the south, but an eroded extinct volcano to the north. And it's an astonishing site to put a telescope. One of the best in the world, certainly in the top 5 observing sites in the world. This is a photograph I took when I was last out there. I do occasionally get to go, which is splendid. And you can see it's covered in telescopes. It's an absolutely incredible place. And the reason it's so good is it's high, it's steep, and it's dark. High means you get up where the air is dry and relatively clear, and you're above the cloud layer. It's steep, which means that the air tends to go around the mountain, the airflow, rather than over it, which keeps the air above it very stable. And it's dark because that's what the law says, that there are very strict rules on La Palma governing the amount of streetlights and light pollution that are allowed, because astronomy is important to the island. And so you get this beautiful sight with incredible skies above you. And there are lots of telescopes, and our telescope, the Liverpool Telescope, is a nice one. It has a mirror 2 meters across. You can get the scale there from the person standing at the bottom, who's my boss. We've got a whole load of cameras on it. There's other instruments, spectrographs, infrared cameras, special cameras for monitoring the sky. But the thing that makes it really special is how it is operated. It's a very fast-moving telescope. It's designed to whip around the sky as quickly as possible. And it's run not by people sitting there telling it what to do, by an automated, sort of almost artificial intelligence scheduling system, which means it can react rapidly to sudden changes in the universe. And that's important because of the kind of science this telescope was designed to do. There are other much larger telescopes around the world. There are other much larger telescopes on the Palma. But this telescope can do science none of the others can do because it's designed to react quickly. And that's important for studying all sorts of areas in astronomy, including ones that lots of people outside astronomy find fascinating. Things like asteroids. This is an asteroid 433 Eros observed by the NEAR probe as it was approaching it. And it looks like a potato. It's actually quite big for a potato, but it's a rock rotating in space. But these are fascinating things. They tell us about the origins of the solar system. They tell us about where the Earth may have come from, because they haven't changed much since they were formed. But they're also potentially dangerous. We have to be concerned about something like this smashing into the Earth at some point in the future. And so all of these questions that are outstanding about these objects are interesting to astronomers, but they're also interesting to anybody. And there's a lot we don't understand. And then another area that is very, very big in astronomy at the moment, but where there are still many unanswered questions, are exoplanets, extrasolar planets. And I've got here a rather nice artist's impression by David Hardy of some exoplanets. And the reason I'm showing you an artist's impression is because all of the observations are rubbish, because they're really hard to see these things. They're faint, they're very far away, and they're right next to big bright things called stars. And so we can't study them in detail yet, but we can detect them, we can find them. And that requires technologies that work in a slightly different way to a lot of other telescopes. Another personal favorite of mine, exploding stars. This is the remnant of a star that was seen to explode about 1,000 years ago. And everybody loves an exploding star. And they like the things that are left over by exploding stars. You've got, in this case, you've got a neutron star, insanely dense, weird kind of matter, all sorts of strange questions associated with them. And of course, some supernovae produce black holes. And if you ever go into a pub or a restaurant or somewhere like that and get chatting to somebody and they ask you what you do and you say you're an astronomer, the next question will be about black holes. Always. Everybody is fascinated by black holes. And one of the reasons is because we don't really understand them properly yet. And so studying these things is important. And these three are random bits of astronomy that I've chosen, but they do all have something in common. And the thing that they have in common is what it is that makes them difficult to understand. And that thing is that they're changing. The changes matter. If you're looking at a galaxy, if you look at a galaxy today and you look at a galaxy in a year's time, it probably won't have changed very much, but these things change dramatically. Asteroids are moving, they're rotating, planets are orbiting around their stars, and as you watch them, you can learn more about them. Exploding stars are obviously unpredictable and sudden. So these changes matter. And to study those changes, you can't just use a normal research telescope because you're not necessarily looking in the right place at the right time. If I'm lucky enough to get time on a big telescope and we're not in the middle of a pandemic, I will travel to where the telescope is and I'll go to the top of the mountain and I'll sit there and I'll use the telescope for 2 or 3 nights, which is great. I mean, fantastic part of the job. But that's pointless if I want to look at an exploding star, because I'll sit there for 3 nights and none will explode and I'll come home again. It's a waste of my time. It's a waste of the telescope's time, which is frankly a lot more important than my time. So what we need is a kind of telescope specifically designed to look at these changes. And that's where things like the Liverpool Telescope come in. This is what we call a fully robotic telescope. It's the largest fully robotic telescope in the world. And it doesn't work by a person sitting there telling it what to do. It doesn't work by a person sitting anywhere telling it what to do. It does most of the work itself. So instead of telling people they've got their 2 or 3 nights and then flying out to Palma, we collect what we call observing programs. These are descriptions of what astronomers want the telescope to do. And they're collected by the Telescope Management Centre, which is an office in a building in Liverpool. We then send them out to Palma over the internet and we go to bed. It's brilliant. And while everybody's asleep or at the pub or at the theatre or whatever we're allowed to do in a year's time, the telescope is doing the work. It's looking at all these things it could be doing. It might be, somebody might want it to observe a star every night for a year to see what happens to it. Somebody else might want to wait until a supernova goes off and then immediately start observing it. Or you might just want to look at a galaxy in a gap between everything else. And the telescope goes through all of those things, all of those possibilities. And from minute to minute, second to second, it decides what is the best thing to do next, what will give us the best science. So it's an optimal observing strategy. We then wake up the next day, we analyze the results, and science happens. And fortunately, because this telescope works this way, it's been able to keep operating right the way through the pandemic. We haven't had to stop operating. Haven't necessarily been able to get out there to fix things when we'd want to. But an advantage of this mode of operation is you don't need to constantly travel to where the telescope is to keep it operating. But the main advantage is you can do science you can't do any other way. You can monitor things night after night after night to see how they change. You can react to sudden changes. If the telescope sees an interesting change itself, it can change what it's doing and start observing it. It doesn't need to get people involved at all. And that means we can really do some very exciting science with this telescope. So that's why it was designed and that's why it was built. But right from the beginning, it had another job. And that job was to work with as many people as possible. Now, a lot of people get to play with this telescope. I work for a university called Liverpool John Moores University, JMU, and we get a lot of time on the telescope because we build it, we own it, we run it. It seems fair. Astronomers in Spain get a lot of time on the telescope because La Palma is a Spanish island and we don't want to pay any rent. But other astronomers around the world also get time on the telescope. Anybody in the world can apply for time on this telescope. And I don't just mean professional astronomers. We have quite a large number of amateur astronomers, so-called. Unpaid astronomers is perhaps a better description, who have had good ideas and they've sent the ideas in and we said, yeah, that's a good idea, we'll do that one. And they've got the data and they've done science with it. But we use it in our degree teaching. We have distance learning courses, we have normal degree programs, and the students get to use a research telescope. But the main thing, as far as I'm concerned, is schools. Right from the beginning, before we even started designing the factory that the telescope was going to be built in, some of the time the telescope was set aside for schools. And that's been my job for the last 20 years, getting this set up and running it. And it's now what we call the National Schools Observatory. And the idea is actually very simple. We wanted this to be as close to what professionals do as possible. So we didn't want people to book a slot on the telescope and control it remotely, because that's not how professionals work. We wanted kids in schools, kids on their mobile phones, teachers, anybody to be guided through choosing their observations, designing their own observing program. That can be very simple, it can be very complicated, but we can help with that. They then send that through the internet to us, and this is our building in Liverpool, the Astrophysics Research Institute. And then that goes out to the telescope. Those requests go out to the telescope along with everybody else's, all of the ones from the professional and unpaid astronomers. And the telescope does those observations at the best possible time. Doesn't care whether you requested it or I requested it or a 6-year-old in Scunthorpe requested it. It will do those observations at the best possible time. They get sent back. We do a quick sanity check to make sure nothing weird happened, like an aircraft going right through the middle of the observation, which happens about 2 or 3 times a month. And then the kids can download it and they can do their own science. So this is genuinely as similar as we can make it to professional observing, but removing some of the unnecessary complexities like exposure time calculations and things like that. Because this is a flexible way of working, we can work with a wide range of schools. So our initial target audiences, the ones we started with, were 8 to 18-year-olds. We don't go above 18 because they then left school and they started to go to universities or work or something like that, and that's not really our job. And we don't go below 8 because they frighten me. But anywhere between that, we'll give it a go. We wanted very strong links to the research that the telescope is doing. And we didn't just want it to be astronomy or even science. We wanted to look at the computing. You know, the telescope is basically a big software problem. We wanted to look at the maths. We wanted to look at the engineering. How do you build a telescope that's reliable enough to keep working like this? So we wanted to bring all of those factors together. So we're not just talking about one aspect of what makes a telescope like this exciting, but all of them. And we really do, since that initial aim, we started to expand those audiences. We work with much younger children than we used to. We've been doing some stuff in nursery schools now. We work for older ones, but we also work with adults. So there's a whole range of different things we can do with all age groups. The kind of things they do can be very simple. This was a class in Portsmouth, actually, who basically we took a lot of observations of the moon, very high resolution, and they printed them out and stuck them together, and then started looking at the moon and seeing what was on it and comparing it to another giant picture at another phase and trying to understand what the moon was about. So that's a relatively simple thing. But we also have students doing research. This was a group who came to our offices in Liverpool and spent a week working with us on a research program. Chris Copperwheat there is talking to them about some exoplanet discoveries that he was involved in and how they can do some follow-up. So there's a huge range in all of this. We try to involve the technology. Some of you may know this gentleman. This is Jay Tate, who runs the Space Guard Centre in Wales. But he came and helped us to work on a Lego version of a robotic telescope. Can we put one together? Can you program a telescope in Lego? And that's a project that's still ongoing, but it's quite an exciting one. We do a lot of teacher training. There's a couple of teachers trying to find asteroids, which is always challenging when you're trying to do it with paper. But we work with teachers both to help them to deliver, but also to tell us what we need to be doing to prepare all of this. So we do a lot of working groups with teachers. But just as importantly, we don't stop at the classroom door. This is something that I'm particularly passionate about. Education doesn't stop when the kids leave the classroom. They may think it does, but it doesn't. And it doesn't stop when they get too old to go to school, or when it doesn't start before they're too young to go to school. Anything can be education if you approach it properly. But you don't expect to go to somebody and say, I'm going to teach you now, rather than you going and doing what you really want to do. You have to bring the science to them. And that, in my case, means working with a lot of different artists, working with them to share my excitement of the science with them, and for them to share their excitement with their audiences. So we've done street theatre. This was a group I worked with called the Science Butlers. In fact, you might see part of my butler outfit behind me, hanging on the back of my door, which I still occasionally get out. And this was going out into shopping centres, onto the streets, and just sharing exciting science with people using household objects like eggs and making cocktails and talking about science. We do a lot of work in art galleries. This was an exhibition I had, a special exhibition at the Tate in Liverpool, but we've also done the London Design Biennale and various other things, worked with artists who've exhibited all over the world, doing all sorts of different ways of just taking people by surprise. People don't go to an art gallery because they're interested in astronomy, but I hope they are when they leave. That's the point. Work with theatre and dance companies. This was a production by a company called Unlimited Theatre, which was about the first human mission to Mars, a very exciting thing. But I've also worked with dance companies and other theatre companies to just try and reach different audiences. We've even done insane things like build show gardens based on astronomy. This was one at the Chelsea Flower Show a few years ago, which won the gold medal in its category. And this was a garden based on dark matter, trying to get across the concepts of dark matter using plants. And it worked surprisingly well. We talked to about 100,000 people, all of whom got quite interested in the science. A couple of 100 million people around the world saw this on television. And we could take people who were interested in gardens and show them that the questions in their head could be explored in ways that they hadn't thought about, and that the universe is a more exciting place than they knew. But our core business is still education in schools. The Schools Observatory and access to the telescope is free to anybody. The university funds it, funds the access to the telescope, funds the small team that run it. There's a team of about 4 of us who run this project. The majority of the extra features are only, unfortunately, for UK and Irish schools. We're working on that, but it's simply logistics. If we open it up to every school in the world, we will run out of telescope. There simply isn't enough night to be able to do all of this. So a lot of the extra features are just for UK and Irish schools. But anybody, whether you're in school or not, can sign up and take some observations with the telescope. The website's very busy, get about 1.5 million visits a year. We've had over 180,000, yes, nearly 180,000 requests for observations that we've dealt with. And as of this morning, there were 15,600 users on the website. So it is busy, it is active, which is nice. And see, this picture here is the very first observation we took for a school. And I like that one because the camera wasn't working properly. The mirror hadn't been fully cleaned. It wasn't a great observation. But the children got that and they took the data and they made that image from the data. They weren't given a picture, they were given astronomical data. And so they were able to bring this image out and see it for themselves, and the excitement on their faces when this thing appeared in front of them and they'd seen a galaxy for the very first time with observations that they took. That is what this is all about. As Carl was saying earlier, pictures help, but taking those pictures yourself, exploring the data yourself, that makes it really personal and really important. So to help with that, we have quite a wide range of different ways that the telescope can be used. There are very simple observing requests. Get me a picture of a galaxy, observe part of the moon. You might want something slightly more complicated. You might want to observe 3 similar objects to compare them. You might want to look at the same thing several times to see how it changes, and so on. And we also run large multi-school projects, which are often driven by a research question which needs help. So a bit like citizen science programs. And Fraser will be doing some workshops about that later in the week. But there's also a lot of things which don't directly involve observation. We have projects involving simulation, we have projects involving mathematics and engineering, but also taking observations that have already been done and learning how to explore them. So there's a wide variety of different ways of using this. This is the main way that you would take observations. This is one of the more advanced versions. If you're With the younger pupils, you'll get fewer options and so on, but you're guided through the process of choosing your observations. You don't need to understand right ascension and declination and filters and exposure times. You can learn about them, but you don't need to understand them to get started. But there's other things. The Discover section on the website is all about exploring and learning by actively doing things. To support that, we have a Learn section, which is essentially a kind of online textbook. It's essentially because when we looked out on the web, on the internet, when we first started doing this and look at what was available, it was all far too complicated for most pupils. You know, if you look at the Earth on Wikipedia, you're going to get lost very quickly if you're 10. So we wanted something which is easier for them to explore and linked into the observations that we were taking. And they're the three core parts of the website, along with the support sections and the teacher support and so on. And you learn a little bit more about those in some of the workshops this week. If you're only going to screen save one slide on this presentation, screen save this one, because these are the 4 sessions we've got. Various people from the NSO team will be looking at the Liverpool Telescope and other robotic telescopes and how you can use them in your teaching. So this talk is just to give you a taster, but these are the ones where you'll really learn how to do it properly. And I just wanted to give a few quick examples of the kind of thing you can do. And I'm starting rather oddly with an observation we didn't take. This is not from the Liverpool Telescope. This is from a much smaller telescope, and it shows half of the moon. Now, we can't see half of the moon with the Liverpool Telescope because it's designed to do research. It's about precision. It's about detail. And so when we observe with the Liverpool Telescope, we see part of the moon, but you see a huge amount of detail. For example, you could look at one crater there, and you can see this crater at the bottom. You've got shadows cast by a mountain in the center. And so we can help you to use those shadows to measure the height of that moon using the software we provided. And depending on how complicated or simple you want that to be, we can help you with the observations. So if you're working with very young children, they're probably not ready to use Pythagoras. So we take the observations at the exact moment that the sun is 45 degrees above the horizon on the moon. So once you've measured the length of the shadow, that is the height of the moon. For slightly older pupils, we can tell them the angle that the sun was above the horizon. So it might be 30 degrees or 38 degrees or 62 degrees. And they have to do a little bit of Pythagoras, a little bit of trigonometry. For the really good pupils, we just say, well, work it out for yourself. We'll tell you when the observation was taken. It's fascinating watching groups of 18-year-olds trying to work out 3 different angles at the same time on the surface of the moon, but they get there. Sometimes they get there with slightly odd answers. I've had pupils who were convinced that the moon that they were looking at was 3 millimeters high, but this happens. I had one who was absolutely convinced that the mountain was so high that when the moon went past, you'd have to duck. But nevertheless, they get there, they learn that they're exploring the data for themselves. But even just looking at a bit of the moon can be fascinating. As a professional astronomer, I tend to think of the moon as a nuisance. Sorry, Bernard. But it is. It's just this bright thing that gets in the way of looking at all the real stuff. Until I started working with schools. And then I started looking at things like this and thinking, oh, that's fascinating. I wonder what they are. And so I came back a few days later and took another observation, and it was completely different. And that took me by surprise. It shouldn't have done. I knew this was going to happen, but to actually see the moon change like that, exactly the same part of the moon between 2 observations, was fascinating. And so now we've got pupils doing the same thing, taking an observation, trying to work out why it's different, learning about lunar phases by actually looking at part of the moon. We can take nice pictures. This is a 3-color observation taken for a student who wanted to look at star formation. And you can learn a lot about star formation. You can talk about hydrogen as the red color. You can talk about dust and so on. But you can also just look at that because it's gorgeous. And I actually think that's really important. A couple of years ago, I went around a whole bunch of colleagues at an astronomy conference, professional astronomy conference, and asked them why they got interested in astronomy. And there were lots of different reasons. Carl Sagan came up a lot. But one of the main reasons was they saw a picture of something that was really nice and wanted to know what it was. And this is a way that a lot of people get interested in astronomy and so on into other kinds of science. And so taking these, what we call pretty pictures, is an important part of what we do. But taking them in a way that the students have to actually bring out the pictures, design them themselves, put them into software to make their own lovely image is in many ways more important than just looking at a picture on the internet. And you can take several observations and see things move. This is from a 4-night campaign looking at Uranus, and you can see the moons going backwards and forwards. And with a bit of work, you can work out which one's which, and you can work out their orbital periods. And from that, you can work out the mass of Uranus. It's not actually complicated maths, but it's very exciting to do. And I just wanted to have a quick go to see whether you could all help me to find an asteroid in this observation. This is an observation that was taken a couple of years ago of an asteroid that was going to get disturbingly close to the Earth. And we were taking some observations to just follow it up. And I suspect of the 100 odd of you out there, about 5 will now have spotted the asteroid, because you will do this for a living. Everybody else will be saying, well, it's one of the dots, isn't it? Bernard is having a really good look. Sorry. And you can't tell, it's just a bunch of dots, unless, of course, you take multiple observations. So what I'll show you next is several observations repeated one after the other. And now suddenly you can see the asteroid. You see a few other bits and pieces, you see cosmic rays, you see everything, but the asteroid is right there in the center. And that's not difficult. That's quite an easy thing to do. And so that's what we have students doing. We take observations where we think there might be an asteroid that we need to be concerned about. And then we get them to find it for us and tell us what they find. And we take that back and we feed the measurements into orbital calculations, and we work out whether or not we do need to be worried about these asteroids. So that's the kind of project that we can have going all the time, where students are genuinely helping us to do our research, but also having fun at the same time. So that's what we do, or at least some of the things that we do. The question we ask ourselves most often is it working? Are we achieving what we want to achieve? Because if you don't know that, you're wasting your time. If you don't check to see whether what you're doing is actually successful and effective, then you might as well not have bothered. So we do spend a lot of our time evaluating what we do. And to do that, we've designed an evaluation framework. And I think this is worth mentioning because it guides not just how we work out what we're doing, but what we do, because we want to be able to achieve these things. And that's based around some generic learning outcomes. If any of you join Stacey Habergan-Mawsom's workshop later in the week, she was the one who came up with these. And these are not just about learning. They're not just about understanding and knowledge and skills development. It's about behavior. It's about emotions. It's about values people have. Can we help to develop different attitudes to science? Can we help to develop confidence? Can we help to develop a feeling that science is of importance to society in people? And so this is what we want to see, whether we're achieving this. And we have a number of ways that we try and assess this. We do the obvious things. We do web analytics, we do social media stuff, all of the usual bits and pieces that everybody does. We have regular user groups where we bring in teachers and where we possibly can, students, to talk to us about what they've done and what they've learned and what they would like to see. But I think in many ways, most importantly, we get other people to find out for us, because we're biased. And we're going to ask questions where we want, unconsciously, we're going to ask questions where we want a nice answer. So we get external evaluation. We pay professional evaluators every few years to come in and actually do this properly. They do case studies, they monitor lessons, they do interviews with teachers and students, they do in-depth surveys that they design. And then they report back to us, and they report back what works, what effect it's having, and what we need to do to make it better. We actually had our latest evaluation report. I got the final version of it a couple of weeks ago. It's about 200 pages, so I haven't gone through it in detail yet. It's going to take a while, but that's going to help us for the next 4 or 5 years to guide what we need to do. And it's also nice to get some positive feedback. I mean, these are some of the feedback we've got in our evaluation reports. It's popular across all our user groups, not just the ones you expect to be interested in this. They saw a noticeable impact on learning by the students. Our learning outcomes were being met, and they were able to measure that. We had a quote from students saying things like, "I feel like a proper astronomer," which is a lovely thing to be told. But also, we're getting external evidence that this really does matter. In one of our evaluation reports, the independent evaluator said quite categorically that they thought this was one of the most significant initiatives in the STEM field linked to a university. And, you know, I was proud to get that, but I also think that we need to know that we're continuing to do that. And we need to understand how that works so that we can continue to improve upon it. So where next? Well, we want to get wider. We do mainly science, a bit of engineering, a bit of maths. We want to go beyond that. We want to go much more into the technology. We want to be able to move into the humanities and the arts so that we can help with that, with teaching in those areas, using astronomy as the tool. We want to go to a much wider audience. A significant number of people, even before the pandemic, were learning from home. They had left school and were just coming back into education in their 50s or 60s. And that's even stronger now that more and more people are being forced to work from home and being forced to learn from home. So we want to get to that wider audience. And we also want to have a wider impact. When we look at the sort of users we've got, it roughly follows the demographic of pupils in the UK, which is good, but it means that we're not necessarily targeting those groups who will gain the most from it. You know, we can work with independent private schools, and that's great. But they've got so many opportunities going for them that probably the impact we're having is relatively small. If we can put more of our effort into reaching schools where everything we do has a larger impact, it's better for us and it's better for society. So that's something we really want to look at. And we're doing that with a number of different targeted approaches. IBSE projects, inquiry-based science education projects, something that Fraser does a lot of work for us on. These are open-ended, non-specific, open-rooted ways of just exploring a science question. And the robotic telescopes are fantastic for this, because if somebody gets to the stage where we don't know the answer, we can get some data for them and they can try and find out the answer. So they're not just helping with research projects, they're creating their own research projects. And that's not going to be every day, but it will happen, and it's starting to happen. We need to have a ramped approach, particularly to the skills development. People start off knowing nothing, and they need to be able to start off with something simpler, and that every time they do it, they get a little bit more skill, a little bit more knowledge, a little bit more confidence, a little bit more enthusiasm. And that's something we need to build into everything we do, not just some of the core activities. And more, I want it to be learner driven. So this shouldn't be us coming along and saying, okay, deliver this lesson, this will help. This should be us coming along and saying, here are all these things that you could do. What do you want to do? What do you want us to do? How do you want us to help this better? And that's working with students, but also working with teachers so that they can tell us what they need and how we can help them to get the most out of what we do for their pupils and their students. So that's one sort of where next, but there's another one that I am particularly excited about. We're hoping to get a new toy. From as little as 2 years' time, we're going to have a bigger telescope. The one on the left here, to scale, is the current telescope. That's the world's largest fully robotic telescope. This is going to be larger, more robotic, and very sexy. You'll notice it looks like it's a different shape. It's sort of squat. And that's because this telescope is not just designed to be bigger so it can look at fainter things. It's going to be faster. It might even be lighter overall because of new materials. The current telescope can, if something exciting happens, it can usually start observing within 2 or 3 minutes, which is pretty quick for a professional telescope. We want to get that down to 20 seconds because there are things happening out there which we didn't even know existed when we started building the first telescope, where those 20 seconds make an enormous difference. You may have seen a lot in the news about gravitational wave sources. And if you stay on for a couple of talks, you'll hear Martin Henry talking about those. And you should stay on because Martin is awesome. But those happen really quickly. And by the time we've detected them, most of the exciting stuff is already happening. So if you really want to see what's going on, you need a very fast telescope to follow them up. We've got things like gamma ray bursts, where in the first minute, they can fade by a factor of 1 million. And no matter how big your telescope is, that's too long. So a smaller telescope moving faster is often better than a giant telescope moving a bit slower. And we've got things like the Vera Rubin telescope, which is an 8-meter telescope with an enormous camera. To give you an idea, some of you may have digital cameras in your phones or something like that. You'll have a chip inside that digital camera, which is about the same size as my little fingernail. The camera, the chip on the Vera Rubin telescope, is too wide for me to hold my hands apart so you can see it on the screen. It's insane. And its job is to find things that change, new things that we don't know about, and it will find them. They're estimating it'll find something like 1 million brand new variable objects every night, which is ridiculous. Now, a lot of those, they'll be able to work out what they are automatically, but there's going to be a small number where nobody will have the faintest idea what they are. The only way to find out is to follow it up, and to follow it up fast. So we're not just designing this telescope, we're working with things like the Vera Rubin telescope to develop systems to automatically tell this telescope, something exciting has happened, go and look at it now, don't waste any time. And so this is really exciting from the science, and it's going to revolutionize what we do in terms of the research that we do. But it also gives us massive opportunities for the education. We'll be able to follow some of these exciting things. We're hoping a lot of the data that's done from follow-up will be public immediately, and we can do educational programs around it. But it'll also mean we'll have a 2-meter telescope, which is doing a lot less, and we can use it a lot more for education. So we're hopefully going to have some time on the big telescope, but also a lot more time on the smaller telescope, 2 meters is still pretty big, to do more and more exciting education. And so we're looking forward to that. But we're going to work alongside the designers and the engineers and the software developers while they're building this telescope, so that we can use that for education as well. How do you design a scheduling system for a telescope where you have no idea what it's going to be doing, or indeed what it might discover? How do you get a telescope so that it moves really fast across the sky and then stops within a tiny fraction of a millimeter so it's pointing in the right direction? How do you deal with wind? All of these questions we can talk about, and their engineering and their computing and their maths questions. And that's something else we can use to share the excitement of building this telescope. And then once we've got it built, the same people who shared in the excitement of building it can share in the excitement of using it. So that's really all I wanted to cover in this very brief introduction. Don't forget about the workshops later in the week in this frankly awesome conference. This is the website. We're on all the usual social media bits and pieces as Schools Obs. And I'll be delighted to take any questions you've got. But if you need to get hold of me, my contact details are easy to find on the NSO website. Just drop me an email anytime and I'll be delighted to help. So thank you very much for listening.
Andy, thank you very, very much. That was a really good insight into how robotic telescopes work and what you can do with them and how educators can get involved. So we have a couple of questions on the Q&A, so I will run through those. Probably the first one I can throw at you is from Alvaro, and he's asking about the height of the lunar mountains and whether you have somewhere you can point him at or some more information about that.
Yes, I mean, we've got basically all of the things we do on the website. There are worksheets and teacher notes and all sorts of that sort of thing. So if you come along to the website and go to the Discover section, you should find a lunar mountain activity on there. If it doesn't suit you, it's not quite what you want, or it doesn't fit you, or the tools don't work for you, just get in touch and we'll see what we can do to adapt it for your pupils, because that's an important thing. Not every school is the same. And so we need to make sure that it works for you as well as for the ones that we were working with when we developed it. But yeah, I just have a look at the website.
Okay, I think you may have covered this, but then again, you can probably just clarify this from Kok Chung Chin. Do you have different telescopes for different purposes? For example, for planetary imaging, for lunar imaging, and for deep sky objects?
To a certain extent, you do. Professionally, you tend to try and find the telescope which will get your research the best. However, what we tend to do more than that is each telescope has multiple instruments. So building a telescope is a big and complicated and expensive task. So you want to build a telescope that's going to last for at least 20 years. But technology improves. So you want to build a telescope where you can change the cameras. We're on our 4th generation set of instruments, I think, on the Liverpool Telescope. So you might have a camera that's very good for imaging galaxies because it's very sensitive. Or you might have another one that's very good at looking at things that change very fast. Or you might have a spectrograph. We've got polarimeters. We've got an infrared camera. So you use different instruments to get the science that you want. Most of the work we do with schools uses our imaging camera. We actually had to make some adjustments to that. You don't design astronomical instruments for looking at very bright things. You design astronomical instruments for looking at very faint things. The moon is not a very faint thing. And it turns out that we simply couldn't open and close the shutter fast enough. We had to buy filters which only let through 1/30,000th of the light. Then we can observe the moon. But we did it because that's important. So yes, you design the instruments to do the science you want and you put them on the telescope that will work best for it. Good question, by the way. Thank you for that.
Thanks, Andy. And one from somebody who is familiar to both of us that we've worked with quite recently. So Hilary is asking if students will be able to use the new telescope.
Yes, we're hoping that they will. We're still working in detail on the instrument setup, so it may not have a camera. It may only have a spectrograph, in which case we'll be using things obviously where you need a spectrograph. But yes, certainly we plan for them to have quite a large amount of the time actually on the telescope to do project work and so on. But that will be supported by a significant amount of time on the 2-meter telescope. Yeah.
There was one that I was going to sort of throw at you, but Jacob has come in and asked a similar question anyway. So I think Jacob's in the USA, and he's saying, how do they go about signing up for the NSO if you're not in the UK and Ireland?
A very good question. If you come along to the website and go to the register page, which is a little button at the top, you've got two choices. You can register as a teacher in a UK or Irish school, and that's only for UK and Irish school teachers. Or you can just register as a user, and that's for anybody in the world. And you don't get as many options. We simply can't afford the telescope time for everybody to do that. But you are able to observe the planets, the moon. We have a selection of deep sky objects which changes from night to night that you can observe. And we're looking at ways of increasing the range of things that everybody can do. But also, as soon as you've registered, you have access to all of the workshops, all of the teaching resources, all of the worksheets, everything like that is available to anybody who's registered as any kind of user. Okay, I hope that helps. If you get lost, again, just drop us an email.
That's very clear. We have one that came through via the chat, which let me just see if I can rewind to it. So from PCL Brown, we saw a picture of a galaxy at the beginning. How is the picture formed from the telescope data? This may take more than the remaining 16 minutes.
No, I can do this.
You see it? Is there a program?
Yeah,
is
I've got
automated?
That. Yeah. What we do is, because it's a professional telescope, the data comes in a format that professional astronomers use. It's called FITS, the Flexible Image Transport System. And there's lots of software out there which allow you to take FITS files and turn them into nice images. Carl, for example, has been doing a lot of work on JS9. In the early days of this, that software was unbelievably difficult to use. There's a wonderful piece of software called IRAF, which is used by all professional astronomers, and learning how to display an image will take you 3 or 4 hours when you know what you're doing. It's a nightmare. So we wrote some software called LT Image, which is still what we use for most of our educational work. And you can download it all free, put it on your computer and run it. It's getting a bit old now. I mean, to give you an idea, it was designed to fit on a floppy disk. So although it's been updated and adapted, it's still quite old. So we're now working on a version of this where we're going to take some of the aspects of JS9, which I know Carl is working on, and we're going to produce a version which is aimed very strongly at education. So a simpler version of JS9 where we can adapt it for primary schools and secondary schools. But all the software is out there, it's all free. So basically, you tell the telescope what you want it to do, you come back to the website when it's taken it, you download the data file, the FITS file, and you put it in the software. And at the moment, that's separate software that you put on your computer and run, but in the future, it will all run within the browser, and you'll just click on it and it will open up the data in your browser window, and you'll be able to manipulate it there. Hope that answers the question.
I think it does. There are a couple more, so Andy will ask you to answer at least one of them, and anything else that comes through via the chat. The final one then for you, and then we'll let you go, is from Paolo Leme, and he's asking if there are any plans to make the interaction in languages other than English.
Yes, there is already a Spanish version, which is run by the IAC, the Instituto de Astrophysics de Canarias, in the Canaries. So there's a Spanish version of quite a large part of the website. What we're doing at the moment is we're working with the National Astronomical Organization in Thailand. And there we're working on a system whereby they can use our educational resources, but they take over the translation. They have a website in Thailand which uses the telescope remotely through us, and they can translate our resources. We don't have the resources to translate our entire website into dozens of languages. We've done some of it in Welsh, there's a Spanish version, and there's this Thai version. But the idea is, once we've developed this tool which allows the Thais to have their own website which uses our telescope, we're going to open that up to as many people as possible. And so anybody will hopefully be able to come along and collaborate with us to develop a website which suits their education system, as well as being in an appropriate language, but they still have the access to the telescope and the software and the resources that we've got. So that's the plan for that. It's going to take a couple of years. We're only a small team, and there's only so much we can do, but that is certainly the plan to get that going, essentially so that we cease to be a National Schools Observatory and become a genuinely international one.
I feel the word global is coming there.
I was careful not to use that. Carl is global. We're merely international.
Okay, yes, we can't aspire to that. Andy, I think we're done. Thank you very, very much for your time. What we're going to do now is I'm going to pass over, I think, back to Gustavo,